We're moving now into section 6.4, which is about irrational and real numbers. I really enjoy this section. I like teaching this section because up until this point in the course, we've talked about any number of different types of numbers. We started with uh, whole numbers, and then we went to integers, and then to fractions, and now we're in decimals, and we're getting to this irrational and real numbers. So we're sort of looking at all of these different types of numbers that exist and the properties that they have. And so this is going to really kind of conclude our conversation about different number types. But we're going to do it in a way that we do some discovery and figure out why we even discovered that these types of numbers exist in the first place. So let's first take a look at an overview of our section. And it is talking about the Pythagorean theorem, square roots, irrational numbers, real numbers, the properties of real numbers. We're adding a new one called completeness, and then operations with irrational numbers. And so we're going to start this by showing a number line. These should look familiar. We talked about them before. They are rational numbers. Rational numbers, remember, are any number that can be written to look like a fraction. And all of these numbers are there. And one of the other things we talked about was that between any two rational numbers, no matter how close they are, no matter how close any two rational numbers are, there's always another one that's in there that you can fit and squeeze between them. We talked about that in a previous video. So just based on that idea, it would seem like there's not any room left for any new types of numbers to squeeze in here, right? Because if we just look at whole numbers, we're talking about these. Once we introduce rational numbers and decimals and fractions, then we can talk about all these intermediate ones. And we just talked about there's no room or there's between any two rational numbers, there's always another one. Again, so it seems like it's full. It would seem like our number line is full and can't fit anything else on it, but we would be wrong about that. There are numbers, there are points on our number line, a random point on our number line that corresponds to numbers that are not rational. If a number is not rational, it cannot be written as a fraction. And the discovery of this concept dates back, probably most scholars think, to the time of a Greek mathematician named Pythagoras, who you probably have heard of his theorem. And Pythagoras had a lot of followers, sort of like a cult following. There were a lot of, back in that time of the 5th century BCE, right? So we're talking about 2,500 years ago. There were religious implications sort of connected to mathematics and philosophy, and all these ideas were sort of intertwined. And so the way people thought about the world was very connected to philosophy and mathematics and religion. Like I said, there was a lot of overlap there. And so as Pythagoras he had a lot of followers, one of the famous discoveries that they made was the Pythagorean theorem. And you probably recognize it, but you might not recognize it like this. Let's discuss this before we go any further. So this picture, in the middle, you see a triangle, right? There is a triangle right there. And it's a very special kind of triangle called a right triangle. And a right triangle is a triangle that has one angle that's 90 degrees. It makes a perfect L shape. Not like that. Let's do better. Makes a perfect L shape. So we put this little box in its corner to indicate that it's a right triangle. And in any right triangle, triangles have three sides. There are two sides that are connected to that right angle. We call those the legs, A and B. And then there's a third side, the side that's opposite from that right triangle. and we call this the hypotenuse. And what you see here in this picture is a square connected to each of those sides, the leg A, leg B, and leg C, or as the hypotenuse C. And if you look at the space that those squares take up, their areas, if you will, the area of A, if you add it to the area of B, is equal to the area of C. And then if you back that up a moment and you think about how the area of a square is actually calculated, you take the length times the width. So the area of square A is the side length. I don't know why I did that. The side length A, this leg, multiplied by itself, A squared, plus the same thing with B, side B squared. And then that equals the area of C, which would be calculated as side C, or that hypotenuse squared. A squared plus B squared is equal to C squared. So we're going to play around with this right here, this formula. And again, this is called the Pythagorean theorem. So we're going to play with the Pythagorean theorem for a moment. So here's a picture of a triangle, a very common type of triangle that's used a lot to demonstrate the Pythagorean theorem. What you'll notice is that it is a right triangle and it has legs of 3 and 4. And so A squared plus B squared is equal to C squared. Again, these are the legs, A and B. So we have a leg A of 3, so 3 squared. We have leg B of 4, so plus 4 squared. And that is going to equal side C of 5, which is the hypotenuse, squared. 3 squared is 9, plus 4 squared is 16, which equals 5 squared, 25. So that's pretty interesting that triangle has that characteristic. Let's now investigate a triangle that we don't know one of its sides, and we have to use the Pythagorean theorem to calculate it. So what you'll see here is a triangle that, again, is a right triangle. It has legs of 8 and 6. And so if we use our Pythagorean theorem, A squared plus B squared equals C squared. Let's call this A and this B. 8 squared plus 6 squared is equal to C squared. Now, let's do these calculations. 8 squared is 64 plus 6 squared, which is 36, is equal to C squared. And then 64 plus 36, if we add them, is equal to 100. 100 is equal to C squared. And we know that 100 is equal to 10 squared. 100 is 10 times 10. And so that means if 10 squared is equal to C squared, C must equal 10, which means the length of this third side is 10. So we just used the Pythagorean theorem to calculate the hypotenuse of a right triangle. We're going to do more. Here's another scenario. See if you can work this one, which is a little different than the previous one. Again, if we use the Pythagorean theorem, I always like to write my formulas down before I use them. Remember that A and B have to be the legs and C is the hypotenuse. In this triangle, 12 is one of the legs, and so is this missing side right here. So we know that, again, it doesn't matter which you call A and which you call B. I'll call this A and our missing one B. So the formula that came already attached to this picture does it a little bit differently, but that's okay. I will do it different. I'm going to do it like this. 12 squared plus B squared is equal to 13 squared. Sorry, 13 squared. C is 13. Our hypotenuse is 13. And so 12 squared is 144. 13 squared is 169. fill in the rest of that equation, and it looks like this. Now, we can, if 144 plus b squared equals 169, then b squared must be equal to 169 minus 44. And that leaves us with 25. Again, 144 plus something equals 169, and that something would be the number 25, which means b squared equals 25. We know that 25 is 5 times 5. So if b squared equals 5 squared, then b has to equal 5. This third side over here, b, is going to equal 5. 5 squared plus 12 squared is equal to 13 squared. Let's do one more. Again, if you didn't get that one, try this one instead. Here is our formula. We will call this A, this B, and this C. So again, we have 16 squared plus something squared, we don't know what, it's equal to 34 squared. Bigger numbers this time. 16 squared is 256 plus b squared, which is equal to 1156. Again, this number must be equal to 1156 minus 256, which is 900. B squared is equal to 900. And 900 is equal to 30 times 30. B squared is 30 squared, so B must equal 30. So this third side over here must be equal to 30. So this is pretty great. It allows us to, again, find the missing side of a right triangle, which is great. There are many different proofs of why this works. There are whole books written with hundreds and hundreds of different proofs. If you're following along on the PowerPoint slides, one of them is even included in there. I won't discuss that here, but I suggest you examine it. One other thing about the Pythagorean theorem is that the converse is also true. Do you remember what a converse is? It's, remember, if P then Q, the converse would be if Q then P, flipping the statements around. And so the converse of the Pythagorean theorem can be stated as this. If the sum of the two, or the squares of two sides of a triangle, equals the square of the third side, then the triangle is a right triangle. Remember I said it had to be a right triangle for this to work? Again, if it works, then it is a right triangle. So again, if you have a right triangle, then the Pythagorean theorem is true. And if the Pythagorean theorem is true, then you have a right triangle. Why is that significant? Because it allows you to form a right triangle, which is very important in building things, which ancient Egyptians were known for all sorts of magnificent constructions. Carpenters may use the fact that they can make a 3, 4, 5 right triangle to make sure things are at a 90 degree. So if you can form something that has these proportions, then you know you have a right angle. And so again, not having any measurement tools to make sure you have a right angle, all you need is this. All you need is an actual physical triangle with those side lengths. So before we move on, I do want to take a note at one of our content standards and talk about something for a moment. So this says in the middle grade, students should also add another pair to their repertoire of inverse operations, squaring and taking square roots. In grades 6 through 8, students frequently encounter squares and square roots when they use the Pythagorean relationship. Now, this is the point in the class where you might say, isn't this elementary, right? Isn't this math for elementary teachers? Yeah, and the stuff we do later in class involves some algebra also. And no, in elementary school, you're not generally doing a lot of algebra. You can see this is grades 6 through 8. You say, why are we learning this? Well, one of the most important things, I think, about teaching anything, but if we specifically focus on mathematics, is you really need to have an understanding of where your students are going. what are they going to be learning next? When you are able to do that, then you're able to know why the thing that you're teaching is important. And also, it might help frame how you teach something and explain to your students why they need to know this particular concept. And so when we see these content standards for higher grades, that's okay that we are learning it, right? Because it is going to matter as we move forward. So we use square roots in this content standard statement. And so let's take a moment to talk about square roots. Square root. What is it? What does it look like? How do we do it? So the square root of a non-negative number is basically defined as a number that, when multiplied by itself, yields the original number. Here's a nice definition right there. The square root of a non-negative number is defined as a number that, when multiplied by itself, yields the original number. So we say that 3 is a square root of 9 because 3 times 3 is equal to 9. If we're looking at this number and we say, what's its square root? What we're asking is, what number times itself equals 9? Okay. Now, it's also important to know that -3, or recognize this, -3 times -3 is also equal to 9. So numbers, positive numbers actually end up having 2 different square roots. They have the positive number and they also have the negative number. But generally, we're usually more concerned about this. There are times when the negative square root does matter, but most of the time we're focused on the positive. And so we call the positive the principal square root. We call the positive square root the principal square root. So let's take a moment and practice this, taking the square root of some numbers. Now, I'll show you a couple, and then also I recommend you try to do as much as you can mentally. You might not be able to on all of them, but I'll show you how to use a calculator as well. So we're going to take the square root. So take the square root of the number 49. And so the number 49, you may be able to just think through it and say, oh, I know that 7 times 7 equals 49. So that means that the square root of 49 is 7. Now, we also know it's -7, but for this exercise, let's just focus on that principal square root. Okay? Now, if you want to use a calculator when you're doing this, I'll show you how to do it on the Windows calculator. And so every calculator is different. For this one, you type in the number first that you want to take the square root of, and then we're going to use this symbol. And I'm going to explain what this symbol is momentarily. Notice how it has this little bar. It kind of looks like a division, but it's angled a little bit, and it's got that little 2 right there. So this is one of the symbols for square root. When you hit it once, you are taking the square root of 49, and it's going to tell you that is 7. So the square root of 49 is 7. Let's try it with a decimal number that you might not recognize. 20.25, 20 and 25 hundredths. Again, if we get our calculator out, 20.25, go ahead and hit that square root button. Now again, your calculator might require you to find the square root button first, and then type in the number, and then hit equals or enter. But it is 4.5, 4.5. Now I want to challenge you to do these next two mentally first, and then maybe double check on your calculator. 0.64 and 1/4. So the square root of 0.64, or 64 hundredths, is 8/10, or 0.8. Remember, when you multiply a decimal number less than 1 by itself, or by another decimal number less than 1, it actually gets smaller. So 0.8 times 0.8 is equal to 0.64. the product is smaller than the numbers you started with. And 1/4. Need to figure this one out. 1/2 times 1/2 is equal to 1/4. 2 times 2 is 4. So the square root of a fourth is 1/2. Now, the symbol that I showed you earlier on that calculator is called a radical sign. So sometimes you'll hear people talk about a radical number. Radical 4 means the square root of 4. And the sign for a radical is this. And historically, it came from the letter R. It evolved from the letter R for radical. R turned into this and then into this, right? You can see sometimes letters evolve into symbols. And so we call this our radical sign. And if we write radical 16, that means the square root of 16, which is equal to 4. And then the last thing we'll talk about in this particular video is this property of square roots that is called the square root squaring property. And it looks like this. It says for any non-negative number b, you can't take the square root of a negative number. For any non-negative number b, if you multiply radical b times radical b, you get b. So the square root of, let's do a different number. The square root of a 5 times the square root of 5 is equal to 5. So let's use that property to calculate some of our own. So we will do this, and we will also do this. So take a moment and try those on your own. So in the first one, we see the square root of 14, or radical 14 times radical 14. Multiplying two square roots, identical square roots together, yields the number that was inside that. Square root of 14 times the square root of 14 is 14. We can also write repeated multiplication using an exponent. This means the same thing as that. So radical 3/2 times radical 3/2 is 3/2. The square root of 2.3 times the square root of 2.3 is equal to 2.3. And radical 0 squared, you guessed it, is 0. So that's an introduction to the Pythagorean theorem, and then also square roots. And we're going to be using those a little bit more in the next videos as we start to investigate numbers that don't really have a nice, neat whole number square root.